I'm just going to be taking you through some notes today. I realized that I don't want to get long-winded, but I have a lot of new information to share with you about waves today. So make sure that you hit pause on this video to go into your Pear Deck and enter the information that's needed to create some notes for yourself for this week. We're learning some new terms. We're talking about the difference between mechanical waves and electromagnetic waves and introducing a couple new terms. Electromagnetic waves. Also, I'm focusing on refraction and talking a little bit about why colors show up in their different rainbows of colors. And then we will use this information to turn them into activities for the rest of the week. And one ed puzzle is coming up this week too. All right. I want to erase right here. I made a little dot as I was going over this before sharing with you. Last week, you learned about transverse waves, their shape and how to measure them. You learned that they have crests and troughs and that they are measured by their amplitude and their wavelength and their frequency. Please continue to go back and review and study those terms. But we're dividing transverse waves into the two categories, one of which you already know. Mechanical is any wave that has to have a medium, otherwise it will not travel. And that is on the left-hand side. Examples for that would be water, ropes, chains, and guitar strings. Whereas today I'm going to be introducing to you electromagnetic waves. It can travel even if there is no medium. That means electromagnetic waves can even travel through outer space. Thank goodness, because the sun's light is our main source of energy, and it is in fact an electromagnetic wave. Fill in the blanks here. Electromagnetic waves are made of electric and magnetic fields. That's where you want to pause the video to stop and type those in, and that comes directly from this term. I'll explain why in a few minutes. But some examples of electromagnetic waves are microwaves. We have cell phone service. We have cell phone radio waves. You can put in visible light. You can put UV rays, gamma rays, X-rays. We have quite a few different categories there, but make sure that you pause the video so that you can type in at least 4 of them, and you'll see them on other slides as well. I'm returning back to our textbook a little bit here just because I do appreciate the information they have. But what I find is that electromagnetic waves are being taught in 3 to 4 different places in the book, and they all explain slightly different parts that we want to understand about electromagnetic waves. This is a review, energy transfer without a medium. Take a look at the question before I get started in reading. How do electromagnetic waves differ from mechanical waves? Now, the answer to that is on the previous slide, but you can also hear it on this page from the textbook. Some waves can transfer energy without going through a medium. Visible light is one example. Other examples include microwaves made by microwave ovens, TVs, radio signals, and X-rays used by dentists and doctors. These waves are electromagnetic waves. Although electromagnetic waves do not need a medium, they can go through matter such as air, water, and glass. The energy that reaches the Earth from the sun comes through electromagnetic waves, which go through space. As shown in Figure 4, you can see light from the stars because electromagnetic waves travel through space to Earth. Light is an electromagnetic wave that your eyes can see. So this page right here is just talking about how electromagnetic waves are different from mechanical waves in that they don't need a medium, but they also have the ability to travel through solids, liquids, and gases. If you can think of light traveling through all 3 of those different examples, then you've got it. Here's where I grabbed a different page in the book. Starting to explain light specifically, this description for light is actually the same description as for all electromagnetic waves, but this was found in the chapter that describes light, and so I wanted to point it out for you. You can see light. It's everywhere. Light comes from the sun and from other sources, such as light bulbs. But what exactly is light? Scientists are still studying light to learn more about it. A lot has already been discovered about light, as you will soon find out. Read on and be enlightened. Haha. Light. Light is a type of energy that travels as a wave, but light is different from other kinds of waves. Other kinds of waves, like sound waves and water waves, must travel through matter. Light does not require matter through which to travel. Light is an electromagnetic wave, or EM wave. An electromagnetic wave is a wave that can travel through empty space or matter and consists of changing electric and magnetic fields. Fields exist around certain objects and can exert a force on another object without touching that object. For example, Earth is a source of gravitational field. This field pulls you and all things toward Earth, but keep in mind that this field, like all fields, is not made of matter. Figure 1 shows a diagram of an electromagnetic wave. Notice that the electric and magnetic fields are at right angles or are perpendicular to each other. These fields are also perpendicular to the direction of the wave motion. Now, as you can see, the red is what they're indicating as the electric field. And in this picture, it's going up and down, where the magnetic field is going left to right. And the existence of these two types of field occurring at the same time is what is causing light to happen. And that answers the question on this slide. But for some of you like me, after even seeing and someone saying, yeah, it's an electric and a magnetic field, you might keep on asking, so what? I don't get it. Why is it causing more energy? How is it able to travel through nothing just because it has those two different fields? This page is where we get into the reason that more work is being done. An EM wave can be produced by the vibration of an electrically charged particle. When the particle vibrates or moves back and forth, the electric field around it also vibrates. When the electric field starts vibrating, a vibrating magnetic field is created. The vibration of an electric and a field and a magnetic field together produces an EM wave that carries energy released by the original vibration of the particle. The transfer of energy as electromagnetic waves is called radiation. Aha. So, okay, now we know electric and magnetic fields are happening together, but here's why. This paragraph gives us that vibration of the particles with that electric and magnetic field, that's what's causing this energy to exist. And kind of the why behind it. But there's that word in yellow that pops out, radiation. And there's a lot of bad vibes that people get from, pun intended, that people are getting from radiation. But maybe you didn't realize that radiation actually is very safe in most cases. It's only when it has very short wavelengths that it can be potentially dangerous to your health, or you are at risk for some side effects that might come with it. The question that we see on here that to answer on the right-hand side, which EM wave has a wavelength, an error there, has wavelengths just short of invisible light. So take a look at the diagram down below. They're saying that if we were to look at all radio waves have, in comparison to the rest of these, they have very long wavelengths. The measure from crest to trough is huge. In fact, football fields long at times. Every time you're measuring wavelengths of radio waves, they're very long. And so as you move to the right, they're showing that in comparison to radio waves, microwaves begin to get a little bit shorter. So in this picture, they're making them a little bit, if you were to get a ruler out and measure, they're a little bit shorter right here. Microwaves still not very dangerous, but they are sending that energy. You're able to cook your food, throw marshmallow in there, and watch that thermal expansion happen. And as we keep on running into wavelengths that are shorter and shorter, now we're getting more and more energy, increasing what those possibilities are. Infrared waves, if you guessed it's related to heat, you are right. If you are using heat lamps to warm up food, infrared goggles, infrared cameras are meant to use heat sensors in order to find or see things. As we get even shorter, keep in mind, infrared, our eyes cannot see infrared waves. But once we get into this little kind of sweet spot area of the wavelength, we call this visible light. Our eyes, all of a sudden, we can see those waves that are moving and traveling to our eyes or away. But once we get just faster than this, or as I should say, shorter in wavelength, we get into waves that we can't see once again. UV rays, those kind of waves that can burn our skin if we're outside or can be damaging. Now all of a sudden we are in short wavelengths that are getting shorter and shorter that are potentially dangerous to our health. X-rays, we have If you've ever gone in for an x-ray, you have a blanket or lead blankets, or the person who is helping you with those goes behind a wall to protect themselves from extra exposure and gamma rays. I apologize. We would have so much more time to talk about all the different types of electromagnetic rays, but I am excited to just talk about these 7 categories. So which one of these has wavelengths that's just shorter than visible light? It would be the kind that gets more energy as well. And so looking forward to see what you put down. So the one that is slightly dangerous or more exposure to our eyes than visible light. Looking for that answer. All right. Now, why? Why do we see different colors when that visible light is coming into our eyes? I want to share with you our very first example of the term refraction. Refraction is what is happening in this picture when white light is going into this prism. This is a triangular tube of glass, and if it was turned a little bit more sideways, we would see that it has that long tube length. But as it goes in white, it comes out as a rainbow. If you've ever had some sort of white kind of angled and cut stone that's hanging in the light, and you'll see that rainbows come out. Or even if you look at a rain shower that's falling from the sky, this is doing the same thing. Basically, what's happening is white light is traveling through air, and air particles are very, very far apart in comparison to glass. And so these wavelengths, they are traveling all together in one thread, as we might say. But when it enters into this new medium, this glass, these particles are so close to one another that they're actually causing those wavelengths to squish closer together, depending on how much they have to travel through. So as the top of the white light has to travel through this portion, the top part of this triangle, it doesn't have as much distance to cover. And so those wavelengths don't get squished as much. And so they come out red. Red is the widest wavelength of all of them, the lowest in energy. It's kind of funny because to me, it seems like it would be if you get slowed down, then the more you get slowed down or the more you have to run through. But it's not about physical running. It's about how squished together these waves are being put. And so the white light that has to travel through the widest distance actually comes out the fastest, the highest energy, the shortest wavelength, and that is right there along the bottom. That is violet. Now, just a little hindsight, as we look at this, the category that comes right after visible light is called just beyond violet, ultraviolet, just faster than it. And the category that is on this side, just less energy than red, is called infrared. And that is not a coincidence. That is intentional. That is on purpose. So talk about these questions, answer them over here. Why does the white light going in come out the other side in all different colors? You can say that it's because of refraction. But if you're not quite understanding the word refraction, just explain that the width of the prism changes the speed of light into all different speeds. Number 2, which color has the lowest energy? Red definitely has the lowest energy. It goes through the shortest part of the prism and comes out with the longest wavelength. Which color has the highest energy? Violet is the color that comes out with the highest energy. So refraction is when a wave changes its speed because it had to switch which kind of medium it was traveling through, and we are going to have some more fun with that. All right, I'm not sure how I'm at on time, but I'm hoping I kept it short for you. Your 2 note cards for this week are going to be, go into Quizlet and take note card for electromagnetic wave. No surprise there. But the other flashcard I want you to create is refraction. Refraction is the word. And careful, there's another word called rarefaction. We haven't covered that one yet, but make sure you do refraction as you make those cards. All right, enjoy your Tuesday. Hopefully you get done, get outside, have some fun, and I'll talk to you later. Bye, kids.